All right, so we are talking about linear functions, and right now we're going to get into a very important aspect of linear functions, which is understanding the slope and its almost identical counterpart, the average rate of change. Okay, so as you see in the slide in front of you, we are looking at the definition of the average rate of change, and I'm just going to go ahead and write the word slope here because they're basically the same thing. So for a function y equals f of x, the average rate of change, otherwise called the arc of the function on the interval a to b, is given by the following formula. So here's your formula to memorize. This is delta. So delta is just the Greek letter for change in math. Whenever you see delta, we normally mean change in y over the change in x. So that's change in. And here's the actual definition: f of b minus f of a over b minus a. Okay. So as this says down here, graphically, this is the slope of the line passing through the points a, f of a, and b, f of b. All right, let me draw a picture to illustrate this. So here is a function. Now I know we're talking about linear functions in general, but for the moment I'm going to draw a function that has some curving going on because it'll make the slope calculation a bit more, I think, easy to understand. So here's some function f. Okay, and let's say that I want to calculate the average rate of change from here, that's going to be a, to, let's say, over here, that'll be b, which is here on the function. And so, sorry, that should have been a line. And so this point here has coordinates a, comma, f of a. And this point has coordinates b, comma, f of b. Now, the average rate of change, as this says, is the slope of the line passing through these two points. So let me draw the line passing through those 2 points. If I can, I'll try to draw this. Yeah, it's reasonable. Okay, so there's the line passing through those 2 points. And, we could let that line continue out here if we wanted to. So this line has a slope. And that slope is the average rate of change from a to b of f. Okay, and so what is it? Well, it is f of b minus f of a over b minus a. So b minus a, that's this, basically it's just this length. That's your run, b to a. And the rise is this length here. So that's f of b, and that's f of a. So that's the rise. So we're just looking at rise over run, which is another definition for slope. Okay. Now, qualitatively, what this means is it's the average change of the function. So if let's say that that this was the model we were studying, what we miss when we look at the average rate of change is we miss all of this stuff here in the middle, this dip down, where it becomes concave down, then concave up, and it's down here. We don't really see any of that if we just look at the average rate of change. We just look at where we end up and where we start. And we end up slightly higher than where we started, and so we have a positive average rate of change. And that's all. So it sort of smooths things out. And sometimes that's useful. Many times that's useful. Okay. So for example, we were looking at this Portland population model. Let's talk about calculating the average rate of change of that function. Now I want to point something out. this function is linear, right? This is a linear function. So if we graph it, it's going to be an upward sloping line. We know this because we did this in the previous lecture. We graphed the line. It starts at 367.1, and then it goes up from there. Okay. Now, another fact, and this is also something we talked about in the previous lecture, linear functions have constant rate of change. Okay, now what that means is that I expect to get the same answer for all three of these. The average rate of change for all three of these should be the same thing. Okay, so if it's not, then we actually don't have a linear function. So let's compute a couple of them. And we could do this in the calculator. In fact, why don't we? Because we already have it. We already have the function programmed, don't we? Yes, we do. So y1 is our function. So I'm going to just actually do this in the calculator. So let's do 0 to 5. So that will be, and the way I'm going to do this is I'm going to do the numerator divided by the denominator. So my numerator is going to be vars, y-vars, function y1 of 5 minus vars, y-vars, function y1 of 0. And notice that I am going to put double parentheses there to close it off so I have the proper number on each side. This is the entire numerator. That's f of b minus f of a that you're looking at right there. And then we're going to divide that, and I'm going to start a new pair of parentheses by 5 minus 0, which is b minus a. Okay. And that, sorry. And look at that, 7.46. Now that number should look very familiar to you because there it is right there, 7.46. It's the slope of the line. So really this is kind of silly. I mean, we actually knew that what this was going to be already. But let's do 3 to 11 just for fun. So again, begin with parentheses, vars, function, y-vars, y1, parentheses 11, close parentheses, minus vars, y-vars, function y1 of 3, close parentheses, divide by, this is just 11 minus 3, but make sure that you put it all in parentheses there. And this is going to be 7.46. It better be, and it is. Okay. Now, the idea is that because it's a linear function, the rise over run is always the same. The slope is always the same. Now, I didn't do 5 over 15, but if you did, you would get the same value. Okay, so what does the slope mean for this function? Well, remember that this function is modeling population as a function of time, elapsed time. And so the slope is the change in population over the change in time. So if it's 7.46, that means 7.46 thousand people per year are added to the population. So every year we gain 7,460 people, or 7.46 people. So we could actually calculate the yearly population increase starting in July 1st. Just by successively adding 7.46 and another 7.46 and another 7.46. Okay. All right. Let's check out another example. Suppose that my distance d in miles from home as I leave work late in the afternoon and head towards home can be modeled by the function d of t equals negative 19.4t plus 12.1, where t is elapsed time. So this is very similar to the one that we just did, except instead of population, it's modeling distance as a function of elapsed time. A couple of other things. Notice that your slope is negative. Now that makes sense actually, because as time is passing, you're getting closer to home, so your distance from home should be decreasing. So we're gonna have a function that is sloping downwards here. Okay. Now to answer these questions, the slope, well, actually we just identified it. It's negative 19.4, and what does this mean in practical terms? It means every hour I am 19.4, I have a change of 19.4 miles per hour. So every hour I'm 19.4 miles closer to home. My d-intercept is this value, 12.1. What does it mean in practical terms? Well, that's my distance from home at time 0. So I start off at 12.1 miles away from home. Okay, so here's a calculator solution for this. Where we've entered the function, then we've calculated our value at time 0. Oh, and then actually, sorry, we're actually answering part C here, so I kind of jumped ahead of myself. So how far are you from home 10 minutes into your commute? Okay, well, one potential mistake you might make here is your time unit. This is in minutes, but the function is in hours. So 10 minutes is what? That's 1/6 of an hour, right? It's 10 over 60 of an hour. So remember that that's going to be your unit in hours that we actually will use for this. This is an input to the function, and so we just want to evaluate the function y1 at 10 over 60, or 1/6 if you prefer to simplify that. And that's what's happening right here. Okay, the t-intercept. So we found the d-intercept. What about the t-intercept? That's, if you forget what's what here, this is t and this is d. So we're going to have some function that looks like that, and we're trying to find that value right there when we cross the horizontal axis. So that's when the function equals 0. So it's mathematically, it's this. So it's the solution to this equation. Now we can solve that. It's linear, so it's pretty easy to just solve that by addition and subtraction. But we could also solve this using calc-intersect, kind of a cheeky way of doing it, but actually this does also give us an opportunity to learn a new technique. Let me pause the video, and then we will come back and we will talk about learning calc-intersect and calc-0.